and welcome to our next section, which is on gradient boosting for classification. So the whole idea is to show you guys that it's really not difficult to extend the gradient boosting algorithm template that we have until now mainly introduced for regression to other supervised scenarios by basically simply coming up with a appropriate loss function for that scenario. So in our case, probably the Bernoulli loss, which is also known as the log loss, or you can also use the so-called exponential loss. Then get out pen and paper, derive a formula for pseudo-residuals, and then run the usual algorithm without the modification. As always, it becomes a bit more complicated if we use multi-class problems. We'll discuss this here also a bit. We then have to basically resort to fitting G discriminant functions in parallel, so kind of loop around a further time, loop around the boosting procedure further time for each of these discriminant functions, but we'll see how that works. It's also not that difficult. So, as I said, the general extension is really simple. We select an appropriate loss function. We have discussed this at length here at this lecture, how our options look like for classification. We said that the Bernoulli loss that is also used in logistic regression is usually a very good choice. You can now decide on your label encoding. So I'm using 0, 1 here, and then we use that form of the log loss, but in the other parts of the lecture, you can also find, first of all, alternative loss functions that could be used, and you can also see the formulations for the log loss for -1, +1 encoding here. And then we take out pen and paper, and we now easily derive the form, the functional form, the formula of our pseudo-residual function. So we take that guy here and compute the derivative with respect to the f variable. This is really simple. I'm not going to read that out. You should be able to do this in, 5 seconds if you are very lazy. Of course, these functions are available in software nowadays. For the most common loss functions, you can just select them by setting a hyperparameter. You can look them up in various papers on gradient boosting. But if we do this and compute the pseudo-residual function for our log loss, also something interesting happens. Because if we look at the structure of this, we see that this is our 0, 1 encoded label minus a formula like this here. So how does this look like? I mean, this looks like exactly the prediction function of our logistic regression model based on a score vector f. Now, in our case here, because we're boosting, this is our ensemble, right? So this is something more complex. But still, we basically do a sigmoidal transformation here of our predicted score, which is on the real axis between -infinity and +infinity, and we transform that through this sigmoidal logistic function here to a probability value between 0 and 1. And the computation of the pseudo-residuals that now is the signed difference between the 0, 1 label and our predicted probabilities. And that actually also makes sense as a residual for classification, right? So if you predict something, or let's say we have a positive example, our class is +1, and we predict a posterior probability of 0.3. So we're pretty strongly off. We have a residual of 0.7. If we have a class of 0 and we predict a posterior probability of 0.1, so 10%, that's not perfect, but pretty close. So this would be a residual of 0.1, a lower residual. And that really does make sense. So in a certain sense, you can see this as a normal residuals between 0, 1 labels and predicted probabilities here when we use the logistic function to transform our scoring function of the boosting model. kind of our regression score, so to speak, to a probability scale between 0 and 1. And that's quite nice, and that does intuitively really make sense. The rest now in binary classification really works as in regression. So there's not much to add here, just to be kind of a little bit careful, or that this might be a little bit counterintuitive, that we really fit regression-based learners now on the inside against our vector of pseudo-residuals with the L2 loss. And I mean, that's directly follows from everything else stays the same, right? And this is really nice because we now, in a certain sense, so gradient boosting is basically a reduction technique where we take nearly every supervised scenario and we reduce this on the inside to regression against the L2 loss, yeah? Because our true loss function that we want to work against is encoded here in the computation of our pseudo-residuals. So that's kind of the only thing that enters the algorithm and enables us now to handle all of these different supervised scenarios. We can also use exponential loss. There's not a super big difference to Bernoulli loss. Usually, at least from my perspective, Bernoulli loss makes a bit more sense from a theoretical perspective, because you can do this maximum likelihood connection between loss minimization and maximum likelihood, and the maximum likelihood perspective. And this is also the reason why we came up with this loss for a logistic regression model. But in terms of practical results, there's not a big difference between Bernoulli loss and the exponential loss. If we use the exponential loss, we can also show that gradient boosting with exponential loss is basically equivalent to Ada boosting. So we can see gradient boosting as kind of a straightforward generalization of Ada boost. There is quite a lengthy discussion in literature whether this argument is simplifying things a little bit too much. We kind of have to abstract away from many other different aspects of the underlying or of the original Ada boost algorithm. But at least through that theoretical lens, we can show that there's at least a very strong connection, let's say, between the two if we use exponential loss in gradient boosting. I now want to show a couple of examples. I'm not sure whether they are super helpful. Let's see. At least I want to show a little bit how gradient boosting and classification now feels. So here I use the ML bench circle data. We sample 100 points from this, so you can see our two circles here with the decision boundary being roughly there. Again, really bad at drawing at all, as always. We now use the Bernoulli loss. We use shallow trees with a maximal depth of 3, and we initialize with a 0 model, I guess here. I don't know. Okay, that makes sense. Maybe we are initializing a little bit worse here than we could have. Here is now a plot of what happens during different boosting iterations. So on the left-hand side, we now simply show the background color. On the left-hand side, I now basically show through the background color our ensemble and its predicted probabilities. And on the right-hand side, I'm showing the predictions of the base learner and the pseudo-residuals. And I guess you can't see the pseudo-residuals very well through the color coding of the points, but at least we can show the structure of our model and the currently added component a bit. So if we now go through this, so we can see here at what iteration we are. You can also see the training error and the test error here, and you can see how this develops and how on the left-hand side the components get added together. And on the right-hand side, you can see the pseudo-residual structure, which kind of on a global level shrinks more towards 0 because we have already explained quite a lot of the variance or parts of the variance through our current additive model. And then you can see here how we always fit these rectangular areas on the right hand side and then add them into ensemble, and we get here these kind of overlaying rectangles, which are combined in a linear fashion to form the output of the ensemble. Now, how do we handle multi-class problems here? This is unfortunately a little bit more difficult. Certain things stay the same, so we still have to compute pseudo-residual functions and so on, but unfortunately we now have to extend the algorithm a bit. So instead of fitting one model, one scoring function, we now fit multiple ones. We've discussed that before, that this is a reasonable approach and that this is used quite often in multi-class classification, and boosting is no exception here. So we now fit for each class f1 to fg one discriminant function, so one ensemble, one boosted ensemble. And we tie all of these things together by putting or pushing our joint score vector of all g scores, which encodes our preferences to predict this or that class, into a probability vector by our good old friend, the softmax function. So now this vector here, these g scores, gets transformed into a probability vector, also with g components, with a posterior probability for each class. And we do that through the regular softmax function, which you now have seen in this lecture here before a couple of times. And we also now pick an associated loss function, which makes sense for this, and this is the multinomial loss. We've also discussed this before. You know how this looks like. This is the formula. And we now compute again the pseudo-residual. So I now do a partial derivative of this guy here with respect to every component score fk. And what do we get out of that? Well, something that looks really, really similar to our pseudo-residual function for the normal Bernoulli or log loss, which was the difference between the 0,1 label and the predicted probability. What we now here have is, well, a dummy encoded variable for our classes. So this is basically a 0,1 label or a 0,1 encoding for class K minus the probability that was predicted for class K. So this is a straightforward generalization what happened with Bernoulli loss in two classes. Here's the algorithm, how it looks like. So we initialize our model. I don't know, here I guess I was lazy, so I initialized with the 0. I guess we can also initialize with the prior probabilities of our classes or something like that. It might make it a little bit more efficient. And here is now this outer loop. No, sorry, not here. So here is the regular loop going through our boosting iterations from 1 to capital N. Here I simply define my formula for the softmax transformation based on the score vector. And here now is this added loop. So that guy here now loops around all of our components models, but what happens here on the inside is really the same as before in our regular boosting template now. So we compute up pseudo-residuals with the formula I just gave you. We fit a regression base learner against that and add it into the ensemble. And the only difference is that we don't have one, ensemble stack where we add in additive components, but we now have G of these ensemble stacks. And in each boosting iteration, we add one additive component into each discriminant function. So at the end, our discriminant functions all would have the same number of additive components, which is controlled by this parameter capital M here. And then at the end, we output all of these guys. And if you want to have probability predictions based on these, you again push their score vector, their joint score vector, through the softmax function. One final visualization. So I don't know, for us, we struggle a little bit with visualizing this very well. So here we opted to use the iris dataset, or a 2D version of iris with sepal length and sepal width on the x-axis. And on the left-hand side, again, you can see in the background the through colorization and alpha blending, you can see the predicted probabilities in various iterations. And on the right-hand side, we try to we try to visualize as good as possible the 3 different scoring functions through overlapping contour lines. I guess we can't see much in iteration 1, so let's go through this a little bit so we can see a little bit more here now. You can see how the probabilities develop, and you can see here these, maybe not that well, you can see here these contour lines of the scoring function. Maybe this is kind of the nicest plot to see something in there. Or maybe even that one here. So you can see here how the scores develop. So this would be the scoring function for, let's maybe call that F3. You can see here the contour lines for, let's maybe call that F1. And that's probably then F2. And I chose my numbering like that. And on the right-hand side, you can see how the posterior probabilities develop, and that at the end, after maybe 100 iterations, we get a pretty nice, somewhat calm and smooth posterior probability landscape for this really simple 2D version of iris.